today we start energy, and we're starting on material for test 4. Okay? Our test 4 will cover energy, it'll cover electrochem and nuclear chemistry. Okay? Now, I keep talking about energy, so we're going to hit energy kind of hot and heavy, and we're going to be picking up parts of chapter 9, okay, and continuing it on to look at chapter 18. So I've kind of mushed them together. So let's talk about what energy is. Remember, energy is the currency of the universe. It's the ability to do work, which means that we apply a force and make something change its motional state, as in speeding up or slowing down. We want to remember that energy cannot be created or destroyed. It can only be transferred or transformed. This is the first law of thermodynamics. We could add to that and really say energy cannot be created or destroyed. It can only be transferred or transformed in a normal chemical process. Okay? As we look at energy and chemistry, we need to first divide the universe into system and surroundings. The system is going to be some small piece of the universe that we're interested in. For us, that's usually the components of a chemical reaction. The surroundings is everything else, including the water that the reaction is taking place in, if it is in an aqueous environment, which for us is the most common solvent, so that's usually a pretty safe bet. Okay? So we can talk about the internal energy, the energy of the system. Okay? Internal energy is the total energy in the system. It's the sum of the kinetic and potential energies of the individual particles that make up the system. If we were in my physics class, we'd talk about the potential and kinetic energy of an object as a whole, like a basketball or a car. Large macro scale potential and kinetic energies, but in chemistry we're usually interested in submicroscopic kinetic and potential energies, the energies individual particles have because they're moving, the energy stored in the bonds. So we're looking kind of at a different scale. So first law of thermodynamics, energy can't be created or destroyed. The total energy of the universe is constant. If we were to look at the total energy of the universe, E universe, we could say E universe equals E of the system plus E of the surroundings. And for any benchtop chemical process, okay, first law of thermodynamics tells us that the change in energy of the universe then would equal the change in energy of the system plus change in energy of the surroundings, which always has to equal 0. Guys, what this means is that any change in energy of the system precipitates an opposite change in energy of the surroundings. So E of the system equals the negative E of the surroundings. If the system then loses energy, the surroundings have to gain. If the system gains energy, the surroundings have to lose. Okay? So if we look at the energy in a system, it can take many forms. Okay? We can talk about mechanical energy, which is macro scale. That's really big. So that's gravitational potential energy, energy due to position above the Earth's surface. So, you know, if I had a bowling ball and I was holding it up, then it would have gravitational potential energy, which is macro scale. If I let it go, the ball starts moving down. That gets changed into kinetic energy of motion. Okay? It's not really the most important forms of energy that we're going to be interested in chemistry unless we're doing an explosion, and the school frowns on me blowing things up. Could be in the form of thermal energy. Okay? Energy in our system could be due to translational and vibrational motion on the atomic level. This is kind of an atomic level equivalent of mechanical energy. And then we have chemical energy, which is the form of potential energy on the atomic level due to plus-minus attractions, and how the atoms are bonded to each other. So chemical energy is stored in weak bonds. And then last but not least is nuclear energy. It's again a type of potential energy or stored energy on the nuclear scale. It's energy due to interactions of in the nucleus. Normal benchtop chemistry does not change the nuclear energy of the system. Okay? We are not building small thermonuclear reactors in here. I couldn't control them anyway. So we can kind of think of our system, okay, and this is more geared toward my physics class, but energy, mechanical equals kinetic plus potential. Kinetic can go to potential, potential can go to kinetic. Kinetic energy macro could go into thermal energy. Potential energy macro can go into thermal energy. Thermal energy could go into chemical energy. Chemical energy can go into thermal energy. So let me kind of redraw this picture a little bit for you, okay? So in chemistry, we think about our system, okay? We're going to have kinetic energy, which we could call thermal, because it's submicroscopic, and we're going to have potential energy, which is due to bonds. This is chemical energy. Okay? Kinetic energy, thermal energy can go to potential to chemical energy. Chemical energy can go to kinetic energy. These are transformations inside the system. So our thermal kinetic energy can go to chemical potential energy. Chemical potential energy can go to thermal energy. It can go back and forth. Okay? Now, along with transformations happening inside a chemical reaction, okay, we can have transfers of energy in and out of our system. So I can have energy coming out, or we can have energy going in. Okay, energy out, energy in. So the energy of our system can change. Okay? So the energy of the system equals energy final, the change in energy of the system is energy final of the system minus energy initial of the system, which is essentially the energy content of the products minus energy content of the reactants. If our system has a change in energy that is positive, then we know that the energy content of our system goes up. This would be energy flowing into the system. If the change in energy of the system is negative, then the energy content of the system goes down and energy is flowing out. Okay? Energy can be transferred in and out of our system in two ways. It can be done by heat or work. Now, hint, work is not a common way that we put energy into a system or take energy out of a system in normal benchtop chemistry. Heat's going to be our primary method. Okay? So any change in energy of the system is going to be the sum of any heat flowing in and out of the system or any work being done on or by the system. Okay? Now, in chemistry, heat is seen more often than work, But in a TNT explosion or something like the combustion of gasoline in a car piston, we can see energy coming out of the system as work. When we do see work, the most common type of work we see in a chemical process is what's called PV work. P for pressure, V for volume. And it has to do with expanding and contracting gases. So work for us is minus delta PV. So work is the negative of the change in pressure times volume. In most processes where gases is involved, remember no gas, no PV work. In benchtop chemistry, we're doing open container things, so that's going to be important. And if we're doing open container things, pressure doesn't change, and we're really not going to have any change in PV. Okay, so if we're doing something in the liquid phase, there's not going to be any work done. Okay, we only see work if we're doing things in a gas phase. Most benchtop chemistry, our energy transfers in and out are done by heat. And heat is a transfer of energy due to collisions on the atomic level. So as we talk about energy and changes in internal energy of a system, we're dealing with what's called state functions. Okay? A state function is a property of the system that depends only on the current state and not how you got there. So, you sitting watching this video, it's a state function. I don't care how you got in the room to watch the video, what you're watching the video on, you're watching the video. Okay? The energy of a system is a state function. Change in energy of the system between two states, okay, is a state function. Pressure, volume, number of moles of gas, temperature are all state functions. What's really interesting is that Q and W, heat and work, are not state functions. They are actually pathway dependent, okay? But the sum of Q and W is always the same no matter which pathway you take to get from one state to another. Really neat. Okay? So the change in energy of the system between one state and another is a state function, and it's the sum of two things that are not state functions. Now, determining the change in internal energy of a system is sometimes really quite hard to do. Work sometimes is very hard to measure, especially in a chemical situation. So, the most common two forms of work in chemistry are electrical work because of the movement of charged particles, previews of coming attractions, and PV work due to the expansion and contraction of the gas. Most of the times, we're doing open beat reactions, so we're under conditions of constant pressure, and we're under situations where we use the second law of thermodynamics and a term called enthalpy. Now, change in enthalpy is looking at the energy moving in and out of the system is very helpful for us. Okay, because it's something that's easier to measure. Enthalpy, okay, symbol H, is related to the energy of the system, the pressure of the system, and the volume of the system. Enthalpy equals energy of the system plus pressure times volume for the system. Under conditions of constant pressure, I can say that change in enthalpy equals change in energy of the system plus change in pressure volume, but if pressure is constant, then I get change in enthalpy is change in energy of the system plus P delta V. For a constant pressure situation, we also know that energy of the system is equal to Q under constant pressure plus W, work under constant pressure is minus P delta V. If we combine those two together, what I get is enthalpy of the system equals the change in heat energy under constant pressure. For a vast majority of situations, if you don't have any gas, the change in enthalpy of the system equals change in internal energy of the system, because no work is done. Okay? Now, this is the case, change in enthalpy of the system equals change in energy of the system, if the reaction involves no gases, or if the number of moles of gas particles does not change. If pressure is not constant or the moles of gases change, then PV work is not zero, and delta H, change in enthalpy, which is sometimes called heat energy, is not equal to delta E for the system. In these cases, as well as Q is very large, okay, it's close enough for what we're dealing with. So in most situations, we're just going to look at change in enthalpy of the system and not change in total internal energy of the system directly. Okay? Enthalpy change is due to heat flowing in and out of the system. So, delta H has a negative value. We call it exothermic. The system loses heat energy to the environment. These are reactions that convert chemical energy in the reaction into thermal energy between the components, and then that thermal energy is passed away from the particles that were reacting, usually into the water in the flask. So the water molecules increase in temperature. Remember that the water molecules are considered part of the surroundings. And then it will eventually leave the flask. So when this kind of reaction happens in a water environment in a beaker, we're going to feel the beaker get warmer, okay? The temperature of the water goes up. In endothermic reactions, delta H is positive. This means the system is gaining energy from the environment. It's pulling energy from the water in the flask. And this water flows into the chemicals, which takes that energy and changes it and stores it into potential energy in chemical bonds. So energy flows in from the water to the chemicals that are reacting, and energy would then flow in from the room. If you were to pick up this flask, it would feel cold to the touch. If we stuck a thermometer in the water before we started the reaction and then after we initiated the reaction, we'd see that the temperature of the water went down. And over time, it would keep absorbing energy from the room. Okay, some special delta H's. Delta H of fusion, the energy change when 1 mole of substance goes from the solid phase to the liquid phase. Its heat of fusion is always endothermic process, so all heats of fusion are positive. Heat of vaporization is the energy change when 1 mole of substance goes from the liquid phase to the gas phase. It's also endothermic, okay? Because you have to absorb energy to make that leap. Heat of formation, delta H sub F, is the energy change when 1 mole of substance is made from pure elements. This is usually an exothermic process. Pure elements want to bond together to complete their octets and move toward a lower potential energy system. So most chemical bonding, most times when you're making a compound from its pure elements, you get an exothermic reaction. Okay? Now, we need to be able to measure the entropy change of a system. So we're going to do this by looking at the heat flow. And to look at heat flow, we're going to look at temperature changes. So we're going to do calorimetry. Okay? A calorimetry experiment is one in which we can examine the transfer of heat between two objects or two parts of a system that are initially at different temperatures, or we look at the heat evolved or absorbed during a chemical reaction in an isolated environment based on the first law of thermodynamics. If I have an isolated environment, energy can move between the parts inside the environment, but it's not leaking any out to the environment around it, or it's not pulling any energy in from its surroundings. We're going to look at two cases. Case one is a constant pressure heat transfer between two objects that are initially at different temperatures, like a piece of metal that's been heated and a container of water that's at room temperature. We know that if we dropped a hot piece of metal into room temperature water, the water would warm up and the piece of metal would cool off until, they reached the same temperature. Now, what one part of the system lost, the other part of the system gained. So the magnitude of the energy lost by the rock or the piece of metal has to equal the amount of energy gained by the water. So the total change in energy of the system, which is the change in heat energy for object 1 plus the change in heat energy from object 2, have to sum up to be 0. So that I can say Q1 has to equal the negative of Q2. Q, the heat change for a object, is equal mass of the object times specific heat capacity for the object times change in temperature. Specific heat capacity is the amount of energy needed in joules to raise the temperature of 1 gram of a substance by 1 degree C. So we get the following equation. Mass of object 1 times the heat capacity of object 1 times the change in temperature for object 1 has to equal the negative of the mass of object 2 times the heat capacity of object 2 times the change in temperature for object 2. So we're going to do a real simple problem, 9.2 on page 375. Okay, let me get back to 375. Let's see. I'm going to do problem 9.3 on page 377. I like it a little better. Okay, so let's look at the problem. Says a block of copper of unknown mass has an initial temperature of 65.4 degrees C. The copper is immersed. A beaker that contains 95.7 grams of water at 22 degrees C. The two substances reach thermal equilibrium at a final temperature of 24.2 degrees C. What is the mass of the copper? Okay guys, when I'm doing a calorimetry problem, when I've got one object dropped into another, I start out by making a table and looking at my two substances. Okay, and I'm going to be looking at the mass and temperature initial, temperature final, heat capacity, and delta T. So I'm going to make a little chart, and and we're going to fill it in. Okay, let's scoot over here. Okay, now the problem tells me that the initial temperature of the piece of copper was 65.4 degrees C. Both objects end up at a final temperature of 24.2 degrees C. Okay, the initial temperature of the water was 22.7 degrees C. And the mass of the water initially, well, the mass of the water is 95.7 grams. Now, the heat capacities are something that we look up. The heat capacity of water is 1.00, let's see. No, it's not 1.0, it's 8.314. But we're going to look up the heat capacities of water and the heat capacities of copper. They're on page 374 in your textbook. The heat capacity for water is 4.184 joules per gram degree C. The heat capacity for copper is 0.385 joules per gram degree C. Okay? Now, let me do the subtraction here. So, to get the change in temperature for the water, I have 24.2 minus 22.7, and I have a change in temperature of 1.5 degrees C. For the copper, I have 24.2 minus 65.4. I have a minus 41.2 degrees C. Okay? I don't have the mass of the copper. That's what I'm looking for. So what I can say is that the Q for the water has to equal the negative Q for the copper. So the mass of the water, 95.7 grams, times the heat capacity, 4.184 joules per gram degree C, times 1.5 degrees C, has to equal the negative of the mass of the copper times the heat capacity, 0.385 joules per gram degree C, times the change in temperature, minus 41.2 degrees C. Okay, so here, so 95.7 times 4.184 times 1.5. So I've got 600.6, and I've got joules equals the negative of the mass times 41.2 negative times 0.385. So a minus 15.862, and that's joules per gram. Okay, the negative and negative are going to cancel out. So I divide through. So 600.6 divided by 15.862. My mass, now when I did this multiplication, I limited myself down to two significant figures. So my mass is going to be 38 grams. Okay? So you ought to be able to do a problem like that. So I'm gonna let you look at that while I fiddle with the computer to switch over to the screen. Now we're going to move on to case 2. In case 2, we're going to be concentrating in on reaction calorimetry. So in reaction calorimetry, we're going to be looking at conditions of constant pressure. And in this kind of calorimetry, the Q of the reaction is going to be equal to the negative Q of the water. Okay, so any energy lost by the reaction is going to be gained by the water. Any energy absorbed by the reaction is going to be lost by the water. So Q of the reaction is equal to negative Q of the water. So Q of the reaction is the negative of the mass of the water times the heat capacity of the water times the change in temperature of the water. If the water warms up, the temperature increases, then the reaction is exothermic. If the water then cools down, the reaction is endothermic. So we're going to look at problem 9.8 on page 387. Okay, in the book. So here comes the problem. So 387. So if we look at the problem, it says the addition of hydrochloric acid to a silver nitrate solution precipitates silver chloride according to the reaction. Silver nitrate plus hydrochloric acid goes to silver chloride solid and nitric acid aqueous. Okay? When you combine 50 milliliters of 0.10 molar silver nitrate with 50 milliliters of 0.1 molar silver chloride in a coffee cup calorimeter, the temperature changes from 23.4 degrees C to 24.21 degrees C. Calculate the delta H for the reaction as written using 1.00 grams per milliliter as the density of the solution and heat capacity is 4.18 joules per gram degree C as the specific heat capacity of the solution. Okay? Now, kind of look over